So let's go ahead and put it all together, as they like to say. So interpreting the regression coefficients. Again, we now have our regression equation. Our prediction for y hat or y prime is the intercept of 20.625 plus or minus, in this case, plus 6.5625, which is the B weight, times someone's score on X. So we need to determine the relationships. So B, or more specifically beta, is fairly similar to R. So it is representing, usually the larger the number, the more significant, and beta itself is often going to be the same as R. The reason, though, that we report beta and not R is that beta and R are going to be the same for simple regression. However, they are going to be different if we're doing more complex multiple regression models. So though a simple linear regression, beta and R would be the same. If you ran a correlation and got R and you ran a beta on a regression, it would be the same number. But we do need to still switch over to the beta to A, let people know we ran a regression, not a correlation, and also because beta later will not necessarily be the same as a correlations are, because we start getting into more complex models that are looking at the interaction between multiple predictors. So again, the unstandardized beta B weight, the standardized beta, similar to R, both of these determine the strength and the direction of the relationship between X and Y. So, but again, we're not actually going to use a correlation table to determine if the beta is significant, because again, we need to create a system that also allows us to look for differences in the significance between multiple predictors. So we're actually going to do a t-test to determine the significance of beta. Now again, when we run this t-test, we will find that if it is a simple linear regression, it is going to have the same chance and it's going to create the same p-value, if you will, as if we had ran a correlation. So again, we are doing an additional step here. We are doing an additional significance test that honestly, in a simple regression, is not necessarily needed, but it's going to be there for consistency to represent that we did run a regression, and it is a test that you'll see when we get to multiple regression we do need to do. So to calculate t, we're going to use the following equation, and this is again building on everything that we have already calculated. We're going to take the B weight, the unstandardized value, so basically that unit change, and we're going to multiply it by the sums of squares x, the square root of that. So we're going to take 64, take the square root of it, and multiply it by the B weight, 6.5625. That's the top of the equation. On the bottom of the equation is going to be the standard error of the estimate. In this case, we calculate that to be 16.77. That gives us a t of 3.1306. Again, APA rounding, we take that to 3.13. At this point, we simply check our chart on the t-test to find out if that is indeed a significant t. So that would give us all the information we want. And again, we have the ability to additionally make predictions. To predict an unobserved score, a predicted y prime from an observed predictor x. We simply plug the x value into the equation and solve. So example, if Cartman spent 4 hours studying for his exam, neuroanatomy, what grade would we expect him to earn? So again, the only thing missing from the equation is x, and x is 4. So we take 6.5625, multiply that by 4, and add it to the constant, a, 20.625. We'd expect Cartman, with 4 hours of study, to get a 46.875. And again, if we were reporting that in APA style, we'd round that to 46.88. Now, we'd also want to find out the confidence intervals. And so for confidence intervals, basically we need to multiply the standard error of the estimate by 0.196. So remember, going back to z-scores, 0.196 is representing the likelihood of someone falling within 3 standard deviations plus or minus on a normal distribution curve. So again, if we wanted to know not only what is the error, but what is the likelihood that Cartman would lie somewhere with 95% certainty. So we're using the standard error of the estimate to go one step further. We're now taking the standard error of the estimate, which gives us a pretty good guess at what's going on, and we're actually multiplying it by 1.96 to bring that standard error of the estimate to the point where it is at a 95% confidence interval. So in this case, we have Cartman's predicted score, 46.88. We've got the standard error of the estimate, 16.77, and we multiply 16.77 by 1.96. This gives us a confidence interval of plus or minus 32.87. So that means that we anticipate Cartman will get a 46.88 on the test, but we're 95% confident that his score will lie between 14.01 and 79.75. Now that's a pretty big range, but that still gives us more information than if we were just guessing what his score would be and we had no data to go by. At this point, we're pretty confident that he'll at least get a 14. And we're also pretty confident, 95% confident in fact, that he will not get a B or higher. The best he can get is a very high C. And we're likely predicting him to get a solid F, 46.88. So again, all we're doing with confidence intervals is we're taking the standard error of the estimate from an estimate of the error to an actual estimate of 95% confidence. And we're changing the name from error to confidence interval. So a lot of times this is what you'll actually see in a prediction. You'll see the predicted score, and they'll either report the standard error of the estimate, you're likely to find the score between these two, or they may take the one step further and give you the confidence intervals. Now again, the smaller the standard error of the estimate, then the smaller also the confidence intervals. So for example, if we were much more confident, if we had a big data set and we were pretty close, we saw a very strong relationship between studying and test score. So much so that the standard error of the estimate was closer to a 5. At that point, then our actual confidence intervals would be close to about approximately 9.5. So we could then say that we know that Cartman would be getting a 46.85, probably no lower than a 36 and no higher than a 56. So you can see how that accuracy can increase if there's less error in the equation. So again, confidence intervals provide a range for the predicted estimate. The final thing we have is effect size. So the effect size here is the same. It's R squared. It's the total variance accounted for in predicting the outcome from the predictor. And again, therefore, 1 minus R squared is the total variability not accounted in the outcome for the predictor. R squared is again an effect size commonly used, and the ratio, notice here, is a little bit smaller than we were talking about when we talked about correlation. So the effect sizes for regression are recognizing that regression is primarily being used to predict human behavior, and that the amount of human behavior that can be predicted by a single predictor is usually not that much. So small here is 0.01, moderate is 0.059 or 0.06, and large is pretty much anything over 0.38, 1.38 or 0.14. So again, R squared is simply Pearson's R squared, and when we calculate a regression, we will get an R as well, and we simply multiply that to get the R squared effect size. So the only difference really here between correlation and regression is that the rule of thumb is a little bit more realistic to predicting human behavior than those rules of thumb when we're looking at correlation, which is used across a broad number of fields of science. So the assumptions of linear regression. Some of these we've already covered, but we're also going to talk about this a little bit more. So first, the relationships have to be linear. And if it's a simple linear regression, it's at one predictor, one outcome, and both need to be continuous, and the relationship between those two continuous variables needs to be linear. 3, the observations between units need to be independent. Residual errors are not related to any other variable randomly. So really what we're talking about is that the errors need to be random. In other words, if there is something that is predicting whether someone is accurate or not accurate in their prediction. For example, if we find people that score very low, we're very accurate in predicting. But the people that score high, we're inaccurate in predicting. That would be an example of residual errors. So the errors at particular levels are related to something. They're not random. Something else is going on there, and it's probably related to performance in some form. We still need both of our continuous variables to be normally distributed, no major outliers, and the estimated error for each unit, the residuals, are normally distributed. So not only are we looking to make sure that the data is normally distributed with our predictor and our outcome, the continuous variables, not skewed, not kurtotic, and no outliers, we also want to make sure, again, that we're capturing that residual error, that estimated error, that it should be approximately normally distributed at every level. The predictor value is fixed. In other words, This really is just a simplistic way to say that it is not a open-ended scale, that there is a scale that we're measuring and that it has a finite end and a finite top level point. There's a top score and a bottom score. And honestly, the variables should be somewhat reliable, which means that they should be stable traits that we're measuring in order for us to predict. So if the variables we're running a regression on are not reliable, they change from day to day to day, then we really couldn't do prediction. So generally speaking, if we're wanting to predict performance from a set of personality variables, those personality variables should not change greatly over time, and performance should be measured in such a way that it does not necessarily change very much over time. So our variables need to be reliable. Now you may have noticed I skipped number 2. Variance is homoscedastic. So this is really catching a lot of what we already talked about as far as points 3, 4, 5, and 6. One of the ways that we can check to see that we're actually not violating these various assumptions is by checking to see if the variance is homoscedastic. In other words, it is the same at all levels, or if the variance is heteroscedastic, which means it varies depending at the level you're at each variable. And what that means, for example, is if at high levels of your predictor, there's not a lot of variance, but at low levels of your predictor, there's a lot of variance, that's going to violate the assumption of homoscedasticity. It's probably going to violate your residual errors assumption, and it's probably also going to violate that 4 normal distributions on the distribution of errors. So let's take a look at what we're looking for in variance and homoscedasticity. So when we're looking at variance and homoscedasticity, we can actually request this from SPSS's scatter plots. Now notice the line of best fit is basically what in any correlation we'd assume is no relationship. And that's because the line of best fit here is not representing the prediction. The line of best fit is simply showing the predictive line and the variance around it at different levels of our predictor variable. So again, what we're wanting to see is something at the top. We want to see homoscedasticity. In this case, no matter where we are in that line of best fit, approximately the error rate between what we predicted and what people actually scored, both high and low, are the same. There's not really much change as we move along that line. A violation would be heteroscedasticity, and 2 examples are shown below. The first one is kind of a bar shape, our barbell shape. So what this means is that the low scores of the predictor, there's a lot of variance. At medium scores of the predictor, there's almost no variance. In fact, we're very accurate at that point. And then as we get to high scores, we actually get more error again. What's more common is what you see here, which is a fan-shaped prediction. And again, this is a violation of the assumptions of linear regression. It's heteroscedasticity. And as your scores in your predictor, X, get higher and higher, you get less and less error. Now, again, these are violations, and if you find one of these violations that is inappropriate to do a linear regression, it's probably representing that you have a nonlinear relationship that's not necessarily being properly captured. So how would you report a multiple regression now that you actually have all of this information? So at first, of course, as with everything, you'd report what you actually ran. A simple regression was conducted. You then wanted to find what it was done on, a relationship between attendance and exam performance. In this case, attendance was statistically significantly related to exam performance. We'd report the actual B weight. Now, notice I've got a large B here, and this is where often we get a little more confusing. Various stats tests report B weight as either a Roman letter B or a small b. I actually prefer small b, but you will often see it as a large b. And then beta is reported as the Latin letter beta or large b. So again, we're going to report the b weight first. Again, remember 2 decimal points APA style. And again, that b is either a small b, beta weight, b weight, or a large b, depending on, again, your preference, honestly. It's reported both ways. It should be italicized. There should be a comma, and then we're reporting beta, and that's always going to be beta. It's going to equal, actually, again, the number that we calculate. And in this case, because it's a simple regression, it would be the same as R. We're then going to report our actual statistical test. And that statistical test is a t-test asking, was beta significantly different from 0? In this case, t equals 67. Now notice that in this case, I'm using a different data set. This is actually not the data set we've been hand calculating from. T equals, and again, our degrees of freedom, which is n minus 2 in this case, so 67. So that means we had 69 people in this study. and it equaled 3.25. We calculated p and found that p equaled 0.002. And again, we calculate our r squared. In this case, r squared. We would have an r in the SPS readout, but also because it's simply a simple regression, we could also simply square the beta. And in this case, r squared is 0.14. And the reason we're reporting an effect size is that we found significance. On average, for every one class attended, students increased their exam score by 3.84 points. And again, that's simply reporting the B weight. So increase tells them the direction of the relationship, and it puts it in clear terms of both the predictor and the prediction. So again, just walking through prediction scores one more time. Once we have that regression equation, we can simply figure out what our actual predicted score is. So if Nancy attended 3 classes, what we'd expect her exam score to be. We again have our A, which is in this case 62.507. We have our B weight, which in this case is 3.842. And again, we have our number of classes attended, in this case 3. We'd simply do that mathematics. By the way, the A intercept in here was actually off the SPSS readout of the example I'm using for how to report regressions. We actually didn't have that value in what I reported in the last screen, but it is always provided for you in your SPSS readouts when you do this in SPSS. So again, we just solve for y. So again, we take 3.842 times 3, we get 11.526. We add that to the constant 62.507. Nancy, we would expect to get a 74.0033 on our test. That's our prediction for her score. So some main points. We use the regression line of best fit to know how much change in the outcome occurs when there's a certain amount of change in the predictor, the IV. We still have a null hypothesis that there is no relationship between the predictor and the outcome. Effectively, our null hypothesis is that the slope of the line is 0. Our beta is 0. And we have an alternative hypothesis. In this case, the predictor and the outcome are related. There is a sloped line, and beta is greater, either not negative or positive, than 0.